All right, I can finally move on to errors. That is chapter 9. Here we go, error handling. And we can close that. Error handling. Rust's commitment to reliability extends to error handling. Errors are a fact of life in software. So Rust has a number of features for handling situations in which something goes wrong. In many cases, Rust requires you to acknowledge the possibility of an error and take some action before your code will compile. This requirement makes your program more robust by ensuring that you'll discover errors and handle them appropriately before you've deployed your code to production. Rust groups errors into two categories: recoverable and unrecoverable errors. For a recoverable error, such as a file not found error, it's reasonable to report the problem to the user and retry the operation. Unrecoverable errors are always symptoms of bugs, like trying to access a location beyond the end of an array. So what they're saying here is that one, errors are a fact of life. They're always going to happen. They're going to exist in your code. Something you got to live with. And that they have two different types of errors: recoverable and unrecoverable. They mention recoverable seemingly like the file example. Somebody threw in the wrong file and thus your program works, but they gave you bad input. So you can recover from that or tell the user they need to put in better input. And then the other type of example seemingly is a bug that you were not aware of, like your program is not working as expected. For example, you're trying to access a piece of memory that does not exist, like you're trying to access an array well outside of its bounds. All right, continuing on. Most languages don't distinguish between these two types of errors and handle both in the same way, using mechanisms such as exceptions. Rust doesn't have exceptions. Instead, it has the type result for recoverable errors and the panic macro that stops execution when the program encounters an unrecoverable error. This chapter covers calling panic first and then talks about returning result values. Additionally, we'll explore considerations when deciding whether to try to recover from an error or to stop execution. All right, so they just laid out the chapter. First, we're going to go over panic, which is unrecoverable errors, and then we're going to go over the result type. And then seemingly somewhere in between, or maybe at the end, we're going to go over which cases should be a panic, which cases should be a result type. Let's continue onward. Unrecoverable errors with panic. Sometimes bad things happen in your code, and there's nothing you can do about it. In these cases, Rust has the panic macro. When the macro executes, your program will print a failure message, unwind and clean up the stack, and then quit. This most commonly occurs when a bug of some kind has been detected and it's not clear to the programmer how to handle the error. And then we have this blurb about unwinding stack. So up here they said something about the process it goes through. So when you call a panic, it executes, right? Your program will print out a failure message. It will unwind and clean up the stack and then quit. So the unwinding the stack or aborting in response to a panic. By default, when a panic occurs, the program starts unwinding. All right, unwinding is here again, which means Rust walks back up the stack and cleans up the data from each function it encounters. But this walking back and clean up is a lot of work. The alternative is to immediately abort, which ends the program without cleaning up. Memory that the program was using will then need to be cleaned up by the operating system. If in your program you need to make the resulting binary as small as possible, you can switch from unwinding to aborting upon a panic by adding panic equal abort to the appropriate profile section in your cargo.toml file. For example, if you want to abort on panic in release mode, then add this. Okay, so what they're saying here is that the panic macro is going to go through a process, and by default the process involves unwinding and cleaning up the stack. That means properly handling any open memory that you have access to, and probably freeing it, right? However, there are sometimes when you don't want to do that. There are times where you want your binary to be as small as possible, And in order to make it small, you do not want to have this extra work of the unwinding, cleaning up. In those cases, you can use abort like they have here. And the abort will seemingly just end the program and then allow your operating system, or depend on your operating system, to then clean up all your memory. I mean, options, I guess. Let's try calling panic in a simple program. So they created a program and they're calling panic, and we can test that out. Bring up my editor. Dun dun dun. And have print hello world, and then after that I can do a panic. Crash and burn. Homage to, I think, the Hackers movie. Put a semicolon at the end. Open my terminal. Cargo run. Alright. When you run the program, you'll see something like this. And we ran it. I have a hello world because I still have a hello world here. And compiling errors. This says compiling panic. Mine does not. That's interesting. The version is the same. Project is different because my computer. Finish time different. But the main thing that looks like it's supposed to be the same is this. So we have a thread main panicked at crash and burn. So it tells us what function panicked. It tells us where it panicked. Crash and burn, which is the message that we passed into the panic. And it gives us the line, which is 3-5. Line 3, I think the 5th character, maybe? 4 spaces, 5th character. Note run with Rust backtrace equal 1 environment variable to display a backtrace. Okay, they'll probably go over that. So let's continue onward. The call to panic causes the error message contained in the last 2 lines. The first line shows our panic message and the place in our source code where the panic occurred, which was right here for us. The second line, 5th character. For them, it was second line, 5th character. For us, it was third line, 5th character. In this case, the line indicated is part of our code. And if we go to that line, we see the panic macro call. So that is right here. In other cases, the panic call might be in code that our code calls, thus not our code. And the file name and line number reported by the error message will be someone else's code where the panic macro is called. We can use the backtrace of the functions the panic call came from to figure out the part of our code that is causing the problem. We'll discuss what backtrace is in more detail next. So what they're saying here is there are 2 possibilities for a panic call, like when you see it down here in your stack trace, right? It could be in your code, where right here we have our line, or it can be in code that you are calling, as in third-party code. And in the case of the third-party code, it's still going to give you the line number and file name, which is this right here, and even the message, right? But it's going to give you the line number, file name, and message of where the panic was called in that third-party code and not your own. What they're saying here is that we can use this backtrace in order to figure out the call stack and find where our code called this code that eventually panicked. So continue onward. Using a panic backtrace. Let's look at another example to see what it's like when a panic call comes from a library because of a bug in our code instead of from our code calling the macro directly. In listing 9-1, this one right here, has some code that attempts to access an element by index in a vector. Okay, so let's write that out. Let v equal vector 1, 2, 3, and then let's access position 99. Here we're attempting to access the 100th element of our vector. I said 99, it is 100. You start counting at 0. My bad. But it only has 3 elements. In this situation, Rust will panic. Using the closing brackets is supposed to return an element. But if you pass an invalid index, there's no element that Rust could return that would be correct. So what they're saying here is that using this syntax, we are expecting to get an element of the vector. However, since this index does not exist within this vector, passing this index into this vector, there is no element that Rust can return back that would be valid. As such, it should panic. Other languages like C will attempt to give you exactly what you asked for in this situation. Even though it isn't what you want, you'll get whatever is the location in memory that would correspond to that element in the vector, even though the memory doesn't belong to the vector. This is called a buffer overread and can lead to security vulnerabilities if an attacker is able to manipulate the index in such a way as to read data they shouldn't be allowed to that is stored after the array. Okay, so what they described in that paragraph is called a buffer overread, which is here. So what they're essentially saying is that if you have a vector or an array, because vectors underneath I believe are arrays, there's a certain amount of memory that has been allocated for you to use for this vector. And currently it's probably like a capacity of, I don't know, 3, 5, something small. But we're trying to get to position 100, which is index, well, position 100, index 99, we're passing it in, right? And this is well outside of our current bounds for our vector. However, in languages like C, if you're attempting to do this, C would see that you have this vector that's of this size. Note that if this vector were to continue and have something at position 99, it'll probably be over here, read that memory, and then return that value. And this is an overread because instead of reading what is this container is, you're reaching past it and accessing that piece of memory. To protect your program from this sort of vulnerability, if you try to read an element at an index that doesn't exist, Rust will stop execution and refuse to continue. So let's try and see. All right, let's run it. And here we go. We have main panicked at index out of bounds. So that was the message they probably have in their panic message. The length is 3, but the index is 99. And Rust compiler, this is the file, seemingly. They have like a hash there. Source libcore slice mod.rs. So that's the file. This is the line number, and this is the number of indices going across, like the character. And note we have a Rust backtrace 1. So in this example, like they were saying earlier, this is us calling code that will eventually panic. And they return the file name, line number, and character count, I guess, of where it started, of where the panic happened. But as you can see here, there is no reference to our code. So seemingly, the next step would be go through the backtrace and get it to run, or get Rust to show us where in our code this happened. This error points at a file we didn't write, libcore slice mod.rs. That's the implementation of slice in the Rust source code. The code that gets run when we use the close brackets on our vector v is in the libcore slice mod.rs, and that is where the panic is actually happening. The next note line tells us that we can set the Rust backtrace environment variable to get a backtrace of exactly what happened to cause the error. A backtrace is a list of all the functions that have been called to get to this point. Backtraces in Rust work as they do in other languages. The key to reading the backtrace is to start from the top and read until you see the files you wrote. That's the spot where your program originated. The lines above the lines mentioning your files are code that your code called. The lines below are code that called your code. I see. So above your code should be, above your line message should be things that you called, and below are things that called your code. These lines might include Rust code, standard library code, or crates that you're using. Let's try getting a backtrace by setting the Rust backtrace environment variable to any value except 0. And they have an example of the output there, but let's do that here. So it looks like we can just set it at the very beginning. Rust underscore backtrace equal to 1 space. And did I misspell it? Hold on, let's try that again. Let me just copy it this time. Oh, I guess I did misspell it. Understood. The key to reading the backtrace is to start from the top and read until you see files you wrote. So let's do that. Start from the top, see files that we wrote. We did not write this. Backtrace. We did not write that, nor that. Panic, panic. Rust unwind, core panic. Panic bounds. Core slice implement. Didn't write anything like that. Allocate to vector. This is lib allocate. We didn't write that. Errors main source file line 4. Let's look up here for a second. It was line 4, so this is us. We are number 12. So the point of all of this was that in the case that we wrote code, that called code, that panicked, we want to be able to find where in our code we called that code that panicked. And what they were saying is we start from the top like we did, we read down until we find our lines, and this is it. This is the line of our code that called code that panicked. This is where we would want to start our debugging process, or at least start thinking about what our code is actually doing. That's a lot of output. The exact output you see might be different depending on your operating system and Rust version. In order to get backtraces with this information, debug symbols must be enabled. Debug symbols are enabled by default when using cargo build and cargo run, without the -- release flag, as we have here. So what they're saying here is that to get this information, this debug information, we have to have debug symbols enabled, and that's enabled by default for cargo build and cargo run. However, if we had the release flag, so if we built with a release flag, I guess maybe even ran with a release flag, we wouldn't be able to do this. We wouldn't be able to see the debug process, or this stuff. In the output enlisting 9-2, line 12 of the backtrace points to the line in our project that's causing the problem, which we did find right here. If we don't want our program to panic, the location pointed to by the first line mentioning a file we wrote is where we should start investigating. Said that earlier. In listing 9-1, where we deliberately wrote code that would panic in order to demonstrate how to use backtrace, the way to fix the panic is to not request an element at index 99, which is right here. So we can fix the panic by let's request an element at index, to say 2. And now if we did this even with backtrace and runs, it compiles, it doesn't do anything. When your code panics in the future, you'll need to figure out what action the code is taking with what values to cause the panic and what the code should do instead. So yeah, that's just part of the investigation process, figuring out why it's panicking, why any of this is happening. We'll come back to panic and when we should and should not use panic to handle error conditions in the to panic or not to panic section later in this chapter. Next, we'll take a look at how to recover from an error using result. All right, so I think I'll just cut this at part 1, and it looks like in the next section we're going to go over the result type, which has, you find out then. But yeah, I hope this was useful. Hope this was entertaining. Good luck with your errors. Peace.